All right, astronomy people, let's talk planetary atmospheres. A few things about planet atmospheres. They shield a planet's surface from harsh radiation from the sun. The atmospheric molecules absorb, a lot of that radiation. So life as we know it wouldn't exist without some of that atmospheric protection that we have. Atmospheres also retain and distribute heat through wind and circulation, and they moderate the amount of energy lost to space because a lot of the molecules absorb that heat energy. Atmospheres also supply needed pressure to keep liquids from boiling away into space. If you were to have a cup of water on Mars, it would actually boil away immediately because there's not enough air molecules pushing down to keep it in liquid form. So thankfully, we have that pressure needed. So we have water in the liquid form here on the Earth's surface, which is necessary for life as we know it. And the two key determinants in determining how thick a planet's atmosphere are temperature and gravity. Temperature is really a measure of the average kinetic motion of molecules. In other words, faster moving molecules equals warmer temperatures. And thus, that's going to generate basically thinner atmospheres because atmospheric molecules are likely to escape off into space, escape the hold of gravity of a planet a little bit easier. Cold planets then have slower moving molecules, thus thicker atmospheres. Likewise, then gravity, the lower the gravity, the easier molecules can fly away into space, and the higher gravity, the more difficult. So your low gravity tends to have thinner atmospheres and high gravity, thicker atmospheres. The smaller the particle, the easier it flies off into space. So if you have a planet with a small gravity or a warm temperature, you're likely going to have just larger high mass molecules such as nitrogen and oxygens and carbon dioxides. They remain bound easier due to their larger size. And so warm and smaller gravity planets have the large atmospheric molecules, and cold and larger gravity planets tend to have large and small atmospheric molecules. This is why we see a lot of hydrogen and helium around the Jovian planets. Speaking of that, Jovian planets have massive, thick, cold atmospheres. Um, and they do have warm surface temperatures due to internal heat, but they're much colder on average than the terrestrial planets, which are much closer to the sun. Terrestrial planets also have smaller gravities, so you would expect thinner atmospheres with uh, collection of heavier molecules like carbon dioxide that you see in Venus and Mars, and then nitrogen, which you predominantly see here on our surface. Here's pictures of temperature profiles of terrestrial planet, which you see in the left here. The temperature usually goes down as you get higher in the sky. Our temperature profile has a little bump because of the um, ozone layer, and then it drops down again, increasing greatly as you get into the thermosphere. And a planet such as Jupiter, Saturn, Uranus, Neptune, the Jovian planets have heat, very high temperatures near the surface, but they cool down very quickly as you get higher into the atmosphere, and then have that thermospheric rise as well. One way, the most efficient way for atmospheres to transfer heat is through the process of convection. And convection is basically hot air rising and cold air sinking. There is conduction, which is molecules colliding when they interact with the warmer surface, but this isn't effective as moving. This is not as effective in moving heat through a gas. Convection is more efficient in that way. And then, of course, radiation is a type of energy transfer that is coming to us from the sun. The sun emits a bunch of solar radiation, and that is absorbed by the atmospheric molecule. Because our planet is spinning, it produces swirling winds. First of all, hot air rising and cold air sinking creates a convection current, which creates winds that blow across a planet. Now, if our planet didn't spin at all, the winds would be great. There would be a great wind from the north blowing down to the south in the northern hemisphere, and vice versa in the southern hemisphere. And this is because air is rising at the equator and sinking generally at the poles because of the temperature difference. But because our planet is spinning, our winds are actually deflected and curved, and they're actually broken up into wind belts, 3 wind belts in the northern hemisphere and 3 in the south. And this whole process of a object moving over the surface of a rotating planet, causing the object's motion to curve, This is called the Coriolis effect. And the Coriolis effect is illustrated here in a couple of different examples on the bottom. But the bottom line is that air is traveling over the surface of our Earth. It's not attached to the rotating surface, and so it tends to look and appear to curve and take a curving path across the Earth's surface. Jupiter has a massive Coriolis effect, producing such strong swirls that there are bands and many jet streams that line the surface of Jupiter. Of course, the Great Red Spot is one of such of these tight swirls. And we already looked at the temperature profile, so I'll skip over those. Mercury doesn't have an atmosphere. It is so close to the sun and has such a low gravity that all the atmospheric molecules have escaped. This creates a situation where Mercury is 425 degrees C on the warm side and minus 173 degrees C on the cold side, causing it to be really a land of extremes. Venus has a very thick atmosphere, mostly carbon dioxide. It holds heat. And so as a result, the surface is extremely hot, so hot that there is no, it's basically clear, there's no vapor to be found there. The surface atmosphere has a orange tint because the blue colors are absorbed by the clouds. But this is Venus. Of course, Earth is clear to visible light, so we can see down the water and ice clouds layers that are swirling due to the Coriolis effect. The blue tint is caused by the preferential scattering of blue sunlight by the nitrogen and oxygen molecules in our atmosphere. Mars is mostly carbon dioxide. It is also transparent to visible light, so you can see down to the surface. It causes the atmosphere to look like it has a reddish tint, but that reddish tint is from the dust molecules that are blowing around in the atmosphere, a lot of oxidized iron in the dust. We would expect to have Mars we would expect Mars to have a deep blue color, but instead it has that pink color from the dust particles. And of course, we talked about some of the necessary things for life on a planet, including an atmosphere that's thick enough to protect surface life from being zapped by ultraviolet radiation. And then, of course, we need more pressure on the surface of Mars in order to maintain liquid water. We think at some point in the past it did have that pressure, but not today. Jupiter and Saturn are both very dynamic and colorful. Saturn's atmosphere is a little bit more muted than Jupiter's, but they're primarily hydrogen and helium with cloud decks of ammonia ice crystals in their upper atmosphere, which give them that tannish color. There are strong Coriolis effects on both planets, Jupiter being the strongest, rotating once every 10 hours. And Uranus and Neptune both have thick cloud decks of methane gases that are basically in ice crystal form. And that red orange color of sunlight is absorbed by the methane, and the blue light is scattered, giving them that pretty blue or faintish greenish tint. Uranus doesn't really have any clouds or bands to speak of because we think it has limited internal heat, so there's not a lot of convection motion, and it's really not rotating very fast. However, we have seen bands on Neptune, and even Voyager, as it passed by in 1989, caught on camera a large dark storm we called the Great Dark Spot. But since then, we haven't found that dark spot on the surface of Neptune when we look at photos from the Hubble telescope pointing at Neptune. But it definitely rotates quickly and has turbulent bands of swirling wind. And that's a look at planetary atmospheres. Next time, we'll talk magnetic fields.